All right, our next chapter, which is the second to last chapter for this semester, is electrochemistry. Before we get to the main part of this chapter, electrochemical cells, we're going to have to do some review, a bit of review of Gen Chem 1, and we're going to also introduce another way of balancing chemical reactions. But let's look at this. Electrochemistry deals with the interconversion of electrical energy and chemical energy. Can you get chemical reactions to produce electricity? All right. And this was going to deal with our redox reactions, oxidation reduction reactions. And because in a redox reaction, energy is released in a spontaneous reaction, delta G is negative, and is converted to electricity, or we'll also deal with the end where electrical energy is used to cause a non-spontaneous reaction to occur. And here's an example of a redox reaction. If you take solid magnesium, throw in 2 equivalents of aqueous HCl, they will react together to get magnesium chloride, which is dissolved in water, and H2 gas. And when we look at the oxidation states, magnesium is 0. Note our H is +1, chloride is -1. Here our magnesium is 2+, so our magnesium goes from oxidation state of 0 to oxidation state of 2+. Chloride is -1, it stays at -1. Hydrogen goes from +1 to 0. So since the magnesium went from 0 to 2+, it gained positive charge. It means magnesium is oxidized to magnesium 2+. And then the hydrogen protons are reduced to H2. Okay, well, let's go back to Gen Chem 1, look at some of these definitions, and look at assigning oxidation states so maybe we could understand electrochemical cells a little bit better. All right, redox reactions. Recall, oxidation is loss of electrons, gain of positive charge. Reduction, gain of electrons, or gain of negative charge. All right. Redox reactions result in a change in the oxidation state. So let's recall how we assign oxidation states or oxidation numbers to atoms. For an element in its elemental form, the oxidation number is 0, and that includes all the allotropes. So oxygen normally exists as O2. So if you have the O2 molecule, both oxygens have an oxidation state or oxidation number of 0. O3 is ozone. But again, even with ozone, all 3 oxygens are in the oxidation state of 0 because it's an element in its elemental form, even though it's an allotrope. Carbon in the form of graphite, carbon's oxidation state is 0. Carbon in the form of diamond, carbon's oxidation state is 0, each individual atom. Okay, and so recall how we write our elemental forms. Most of our elements are metals, and we just write the symbol for the metal. So if you just see Fe without any plus signs or anything by it, +2, +3, that means it's Fe0 in the 0 oxidation state, Fe metal. Carbon is just written as C, copper. Remember, H2, O2, N2, F2, Cl2, Br2, I2. On the periodic table, it kind of goes across the top and then down the halogens. P4 and S8, although note that oftentimes we are just going to write sulfur instead of S8 just as S. All right, the next rule, monatomic ion, is the charge of the ion. If you have Ca2+, the oxidation state is 2+. If you have manganese 4+, the oxidation state is 4+. Oxide is 2-. Chloride is 1-. That's the oxidation state, the charge in a monatomic ion. Monatomic meaning 1 atom. If you have a compound, this is where things start to get tricky and we have to start looking at rules together. In a compound, fluorine is always going to be -1. Remember, a compound is 2 or more different elements bonded together. So if you have NaF, we know fluorine is always going to be -1 oxidation state. Note, chlorine and bromine are usually -1. However, they can be positive occasionally. Oxygen, this is where we're going to get fouled up a bit because we've got this word usually. Oxygen is usually -2. So if you look at H2O, oxygen is -2, carbon dioxide, oxygen is in the -2 oxidation state. However, we're going to find out it can be other oxidation states, or you should have found out in Gen Chem 1. So oxygen is going to be usually -2 unless you work it out as -2 and it just doesn't work. And then it's going to be okay, then it can't be -2. Hydrogen is +1 oxidation state, unless, of course, it's the H2 molecule, in which case it's a 0 oxidation state. But if it's in a compound, it's going to be +1, unless it's with a metal ion, then it's -1. For example, H2O, each hydrogen here is in the +1 oxidation state. Note, if we go to rule D, the oxygen should be in the -2 oxidation state. So if oxygen's -2, that gives us a 2 minus for the oxygen. H2, if each one is +1, 2 minuses, or we've got the 2 minus for the oxygen, 2 plus 1s for the hydrogens, means that this works out to no overall positive or negative oxidation state. And since there's no charge on it, that's what we'd expect. MgH2, note magnesium should be Mg2 plus, it is. Our hydrogens then have to be -1 because they're with the metal ion magnesium. So 2 -1 charges, a 2 plus charge works out to no overall, or excuse me, it's not charged, it's oxidation state. For magnesium, the charge is the same as oxidation state, but this is Mg2 plus oxidation state. 2 -1 oxidation states lead to no overall pluses or minuses, so it's neutral. That's what we'd expect. And note the sum of all oxidation numbers equals the charge of the ion. No charge of these guys on these guys, so we'd expect all the oxidation states to add up to 0, which they do. Here's some examples. You might want to work through them. I'll just work through a couple of them. If we start with the first one, we've got HNO3. Is there anything we know? Well, we don't have any rules for nitrogen, so let's put that guy off. Hydrogen. Well, we know hydrogen is usually +1, so I'm going to assume hydrogen is +1. That's just my assumption right at the beginning. Oxygen. Well, our rules for oxygen is usually -2, so not knowing anything else, let's just assume that the oxygens are -2. Note, we have 3 oxygens with -2 oxidation states, so 3 at -2 gives us a -6. Hydrogen is +1, so we've got that +1. Well, if we've got -6 and +1 here, but HNO3, nitric acid, is neutral, that means that to overcome this -6 and this +1, we need an additional +5 to give us +6 here to counteract that -6. Can nitrogen be +5? Is that a possible oxidation state for nitrogen? Well, if we look at the periodic table, we see that yes, indeed, nitrogen does have 5 valence electrons. Since nitrogen does have 5 valence electrons, it can be in the +5 oxidation state. So we're pretty good with saying hydrogen is in the +1 oxidation state, nitrogen's in the +5 oxidation state, and each oxygen's in the -2 oxidation state. Further along, which one do you want to do? Okay, let's do this one. This is a beast here. H2Cr2O7. Well, where do we want to start? Well, our rules say hydrogen should be in the +1 oxidation state. Since we have 2 of them together, that gives us an overall +2. Oxygen, well, it could be anything, but it's usually -2. So for right now, let's assume oxygen is -2. And but if we've got 7 -2s, that makes this -14. So what does each chromium have to be to counteract this to make this neutral? Well, -14 and +2 gives us a -12. So those 2 chromiums together must be +12. +12 and +2 is +14, needed to counteract the -14. So if 2 chromiums are +12, that means each chromium must be +6, because 2 plus 6s makes +12. Does that work? Can chromium be +6? If we look at the periodic table, we find yes, indeed, chromium has 6 valence electrons, so it can be +6. This is the highest oxidation state chromium has. And that because chromium has such a high oxidation state, it really wants electrons, makes chromium 6 plus very, very toxic to people. But this all works out. Plus 1 oxidation state for H2, plus 6 for the chromium. Each chromium is plus 6. Each oxygen is minus 2. Note, you can't have some oxygens being minus 2 and others being minus 1. Each element in the compound has to have its same oxidation state. If you've got 2 chromiums, one can't be plus 3 and the other plus 2 or anything. They both have to have the same oxidation state. All right, let's go to H2O2. Well, where do we want to start here? Okay, let's start with our H2. It's in a compound, the hydrogen's in a compound, and there's no metal, so that hydrogen should be plus 1 oxidation state. We have 2 of them, so that should be plus 2. We can, well, oxygen, it's usually minus 2, so if oxygen's minus 2, we've got 2 of them, that's minus 4. Wait a minute here. 2 oxygens. If each one's minus 2, because oxygen is usually minus 2, that gives us minus 4. Hydrogen gives us plus 2, and plus 2 and minus 4 don't equal out to neutral. So the next question, can hydrogen be a different oxidation state? Well, it's not with a metal, so it can't be minus 1. Could hydrogen be plus 2 oxidation state? Well, we look at the periodic table. Hydrogen only has 1 valence electron. Heck, it only has 1 electron total. So there's no way to get hydrogen in the plus 2 oxidation state. If it only has 1 electron, it could give up. So since hydrogen can only be plus 1 here, then this has to be plus 2, which means together our 2 oxygens can't be minus 4. They have to be minus 2, which means nope, each oxygen is minus 1. So for the hydrogens, the oxidation state is plus 1. Each oxygen is minus 1. And this is what I mean when I say when you're looking at oxygen, you just look what it has to be. Because we'd assume it's minus 2. If it just can't be minus 2, well, then we have to assign a different oxidation state for it. And this can get a little crazy at times because, let's look at this, KO2. Well, note, we've got potassium and oxygen. This is an ionic compound, so we know that our potassium is potassium plus 1. That has to be its oxidation state. Only has 1 valence electron. It's ionic compound, so this is plus 1 here, which means if our potassium is plus 1, our oxygens together must be minus 1. But there's 2 of them. So how can 2 oxygens together be minus 1? If each one is minus a half. So the oxidation state for the oxygen, each oxygen in KO2, each oxygen has an oxidation state of minus 1/2. Has to be that way because potassium can only be plus 1 because this is an ionic compound. All right, so those are our rules for oxidation states. Remember those. A few more definitions. When you have a redox reaction, you have to have the oxidation and the reduction both have to be happening. So note in this very simple redox reaction, the calcium is just written as calcium. It must be calcium metal then, so it's in the 0 oxidation state. O2 is, well, that's oxygen in the elemental form, so that's the 0 oxidation state. CaO, well, this is an ionic compound, a metal and a nonmetal, so we know the calcium in CaO is 2 plus, which means if it's 2 plus, this oxygen has to be minus 2. Note, each calcium loses 2 electrons. If it loses 2 electrons, that means the calcium gets oxidized. And the thing that gets oxidized we call the reducing agent. So calcium gets oxidized because it loses 2 electrons. But since it gives those 2 electrons to the oxygen, it reduces the oxygen. The calcium reduces the oxygen. Therefore, calcium is the reducing agent, and it gets oxidized. Each oxygen gains those 2 electrons, so the oxygen gets reduced. And because it gets reduced, because it takes electrons away from the calcium, it oxidizes the calcium. O is the oxidizing agent. And this is a fairly straightforward reaction here for a redox reaction, but a lot of our redox reactions get a little nasty. Let's look at this one down here. Copper solid plus 2 nitrate ions plus 4 hydronium ions go to copper 2 plus 2 NO2 gas plus 6 H2O liquid. Note this is balanced. If you add up all the hydrogens, oxygens, nitrogens, coppers, it's a balanced chemical equation because what's given to us balanced. We note, looking at all of the oxidation states of everything, well, copper is 0, nitrogen is in +5 because, well, let's look at this. At first, we assume each oxygen is -2, so 3 of them means -6. But the overall nitrate has a -1 charge, so -6 and +5 for the nitrogen give us an overall -1 charge. So that's what we need. Each oxygen is 2 minus, because 3 of them make -6. The nitrogen is +5, because -6 and +5 give us an overall -1. Can nitrogen be +5? Yes, it can. It has five valence electrons. And we go through assigning the oxidation numbers to everything else down the line. And we see copper started at 0, copper ends at 2 plus, copper gets oxidized. Nitrogen ends at +5, nitrogen starts at +5, nitrogen ends at +4. That nitrogen's getting reduced. Oxygen starts at -2, -2 here, it's -2, it's -2 here. Okay, nothing happens. Oxygen. Hydrogen starts at +1 and it ends at +1. It's good, and we already counted our oxygen. So copper is a reducing agent since it gets oxidized. We say the nitrate is the oxidizing agent because the nitrate gets reduced. The 2 nitrogens get reduced to 2 nitrogen 5 plus get reduced to 2 nitrogen 4 plus. 2 electrons find their way from the copper to the nitrogen. All right, but here's the deal. If I had gave you this reaction without the stoichiometry, I just had calcium plus O2 goes to CaO, you could probably balance that pretty easily. But what if I gave you this reaction and asked you to balance it? All of a sudden things get a little trickier here. So before we can get to electrochemistry, now that we are the electrochemical cells, being as we understand the rules of oxidation numbers and redox reactions, we need to figure out how to balance redox reactions. A little hint, it's not exactly easy. It's not too hard. I'm sure you can handle it, but it's not as straightforward as what we just did up here.